All right, so exponential k is nice because it's almost identical, or it is identical as exponential growth, but now we're decreasing. But the problems are going to set up almost identically, right? So in this one here, we have radioactive elements. We have a decay constant, right? Instead of a growth constant, it's a decay constant now, and that's going to be called lambda. And so for strontium here, strontium-90, our decay constant is 0.0244. Okay, and one thing we should know is that with decay, I didn't talk about it up here, but our exponent with decay is negative. And what's interesting about that, or what makes it difficult, is down here our lambda is really supposed to be a negative number, but through convention, scientists or whoever decided to say lambda is always going to be positive. So our equation becomes the population, or the amount of strontium in this case, is based off the initial population, just like before, times e to the negative lambda times time. Okay, so we make it a positive number, but then we make it negative, we plug it in. I am not sure exactly where that comes from, but that's what we're going to have to deal with as we do these problems. So luckily though, it's exactly the same, right? We want to know when it's half of its mass. So if again, we don't know the original amount, but I can say, oh, the original amount's 1. So then the final amount is half of that, or 1/2, or 0.5, because it's going to be a little bit easier to work with. All right, and so then what we get is that 0.5 is equal to 1 times e to the negative 0.0244t, and I want to know, well, what time was this true? All right, so just like before, I take the natural log of both sides. The reason I do that is that this right side of the equation becomes just that exponent, right? So we just get negative 0.0244t. All right, and so we have a negative number here. One thing to note is on this left side, this natural log of 0.5, anytime you take the natural log of a decimal, it's going to give us a negative number. All right, but we finish up this problem and we get time is going to be the natural log of 0.5 divided by negative 0.0244. Okay, natural log of 0.5 is going to be a negative. The negative 0.244 is going to be a negative. So when we actually calculate that out, we get an approximation of 28 years. Okay, and that's going to be what we call the half-life of strontium-99. So after 28 years, we have half as much left. All right, so what we see in this next problem is that we have radioactive carbon, and this is where, if you ever heard the term carbon dating, this is where it comes from. Right, so we can look at the amount of carbon on something and find its half-life, or if we have its half-life, we can know how much carbon tells us how old it is. All right, so with a half-life problem, we want to find its decay constant. So in this case, it's asking us to find lambda. What is lambda? Okay, and what we're going to do is say the same idea we just did above, right? We have the half-life, so I know that, well, if my initial population is 1, don't care how much it is, I'm going to say 1 of a whole, then that's the initial, then the final population will be 1/2, or 0.5, when time is equal to whatever that half-life was, which was 5730, okay? So I set up the exact same equation, right? 0.5 is equal to 1 times e to the 5730 times negative lambda in this case. All right, and this is exactly the same, except for now we're finding the other variable instead of the time variable. All right, we do the exact same thing, take the natural log of both sides. Technically, you're supposed to divide by 1 here. I'm just skipping that step because it doesn't do anything. When I take the natural log of this left side, I just get negative lambda times 5730, divide by 5730, and I get negative lambda, is equal to negative 0.00012, which tells me lambda is equal to 0.00012. All right, if one's negative, the other's negative, I can just get rid of both negatives. All right, so that found our decay constant. All right, and the cool thing about this decay constant, this is the one that we actually use, or not me or us, but scientists actually use to carbonate things, right? So they can look at something that has 10% of the carbon on its person or its thing, usually dinosaur bones is what I know about, or pottery or something like that. Look at how much carbon it has. They use this decay constant to figure out, well, how many times is it half-lifed? Kind of like you're going to do this next problem. And once you know that, you can figure out, well, how old is it exactly? Okay, so on this next one, it's pretty tough. It requires you to find the decay constant and then think about what happens every 8 days. Have you tried on your own? But then if you look on Canvas, there is a completed copy just to kind of check your notes.